Okay, this is a video for the calculus exam on limits, and there's 30 problems. I'm covering everything you've seen throughout this unit. A lot of it is very straightforward. In fact, some direct substitution stuff, algebra 1, and then we get abstract a few times. So with our continuity and domains and special trig limits and stuff like that. Now, the idea going into an exam is, you know every concept and get the problems everybody gets right. And then make sure on the more abstract stuff, you're showing me everything. And let's say you don't get it 100% right, show me what you know so I can give you some partial credit. I think you guys are going to do a really great job. So let's get going. So the first problem is simply find a limit numerically. Now, and again, look at how the text wrote this. That's not exactly how I'd put this into a calculator. So you have to think about how you would do this on a calculator. And, these brackets right here are really not necessary, but you do need your numerator in a set of grouping symbols. So I wouldn't put this into the calculator the way I saw it right here. I would put maybe a bracket on the outside left and another close that bracket on the outside right. Okay, up top there. So just think like a calculator and double check things. All right. So x is approaching 0 numerically. We're going to put that into our function as y sub 1 very carefully. And then your x values have to approach 0 from the left, and then they have to approach 0 from the right. And we like to do this with symmetry so we can clearly see our limits. So I would go negative 0.1, negative 0.01, negative 0.001. And you could put 0 in if you wanted, and you'd show an error here, but you don't have to. And then from the right, 0.1, 0.01, and 0.001. So what are these outputs right here? Well, it looks to me that we are approaching a limit, and that limit appears to be from the left, negative 1/4, and also from the right, negative 1/4. So I would make the statement like this. The limit of f of x as x approaches 0 from the left is negative 1/4. The limit of f of x as x approaches 0 from the right is also negative 1/4. Therefore, we can say that the limit of f of x as x approaches 0 equals negative 1/4. There's your first problem. The error would be on your calculator, so just be very careful how you put the function into your calculator. Number 2. Now we're going to use a graph. And remember, when you find a limit numerically, you need to show me your table. If you find a limit graphically, you need to show me your graph. Okay, and we could do this analytically too, I believe, but they want to see the graph right here. So let's just put this into our graph, y sub 1. And, looks like I might have done a standard window there. And that looks very linear, but as x approaches 0, isn't my divisor undefined? So there's actually going to be a hole there at x equals 0. So that graph would be much more appropriate right there. But now, okay, so we're undefined at x equals 0, but let's talk limits. So the limit of f of x as x approaches 0 from the left, well, it appears that I'm getting closer and closer to negative 2. And the limit of f of x as x approaches 0 from the right, it also appears from this direction that I'm getting closer and closer to negative 2. And since the left-hand limit equals the right-hand limit, we can make the statement, the limit of f of x as x approaches 0 appears to be negative 2. And a little statement down here that is not necessary. F of 0 equals, well, that does not exist, so we do know that this is not a continuous function. F is not continuous, but all they ask you to do is find the limit over here. I'm just taking more advantage for more learning. Okay, now graphically, I think that's the same function, but now x is approaching negative 1. Now, it looks to me like the hole is at x equals 0, so we could find this with direct substitution. But they ask you to do this graphically, so you need to show me the graph again. All right? And as x approaches -1, I am right here. And that appears to be an output of -3. And I think I'd get that if I did direct substitution too. But let's just do what they asked us to do. The limit of f of x as x approaches -1 from the left-hand side. Looks like I'm getting closer and closer to -3. And from the right-hand side, again, I'm getting closer and closer to -3. So now we can make the statement, because the left-hand limit equals the right-hand limit, that the limit of f of x as x approaches -1 equals -3. All right. And let's talk about continuity and stuff. So f of -1 does equal, so if I did do this direct substitution, I'd get a 1 plus 2 is 3 over -1. That looks like a -3 to me. Therefore, f is continuous in the neighborhood around x equals -1. All right. Obviously, there's a hole right here at x equals 0, but in this neighborhood around x equals -1, the function is continuous. Number 4, f of x minus 3 is just a polynomial, and polynomials are all continuous. Therefore, we can do direct substitution. So this is the stuff I'm doing in Integrated Math 1 right now. X is approaching 2. 5 times 2 is 10. 10 minus 3, that would be a limit of 7. All I did was my basic limit laws right there. Okay? And you could have divided this up into 2 separate limits, but why? In any polynomial, if you ask me to find the limit, I'm just going to do direct substitution. Same thing here. This is a polynomial in factored form, but it's still a polynomial. So it's continuous. I can do direct substitution again. I see a 10 minus 3 is 7, and then a 6 plus 5 is 11. 7 times 11 looks like a 77 to me. There you go. Number 6. Okay, now this rational expression is undefined when t equals 0, but t is approaching 3 in my limit. So again, direct substitution. 9 plus 1 is 10. That's a 10/3. Okay, now here I have 2 discontinuities. I believe one would be a hole and one would be an asymptote. And so we're going to do this one analytically. Okay, so you agree that the divisor is factorable, and one of the factors would be t plus 2. That's indeterminate form. Let's do this analytically. So factor t squared minus 4, well, that's the difference of squares. Won't that be t plus 2 times t minus 2? And your t plus 2's cancel out. So we have a 1 over t minus 2. And now I can do my direct substitution and get a 1 over -2 minus 2 more. That's a -1/4. Number 8. Again, numerically, be careful how you put this into your calculator. All right. I don't want this bracket here. I might bring this bracket out here on my calculator because I need to put my numerator within grouping symbols. So carefully put it into your calculator, and then we have the same inputs to find this limit numerically. So you see how I did this on the calculator? I'm just taking the entire numerator and putting it within grouping system symbols and then dividing by x. And there's my same inputs approaching 0 from the left and from the right. And does it look to you like the left-hand limit equals the right-hand limit? That's what it looks like to me. So I'm going to say the limit of f of x as x approaches 0 from the left is -1. The limit of f of x as x approaches 0 from the right is also -1. So we can say the left-hand limit equals the right-hand limit. Therefore, the limit exists. So that implies f of x as x approaches 0 equals -1. At least that's what it appears to be. And that's all we can do numerically. Number 9. Analytically here again. Okay, and again, if they do not tell you to do it numerically or graphically, they're expecting you to do it analytically without a calculator. So you need to show me that you can factor the sum of two cubes. And I'll bet you one of those factors is going to be x plus 5. What do you think? So f of 0, if I do my direct substitution, I'm going to get a negative 125 plus 125, which is a 0, over negative 5 plus 5, 0. 0 over 0, it's indeterminate again. Wait till I teach you L'Hopital's rule, you're going to love it. Anyway, right here we've got to do this. Okay, what are the factors of the sum of two cubes? Well, a cubed plus b cubed would be a plus b times a squared minus ab plus b squared. So let's factor. So a plus b then here would be an x plus 5, which you notice the common factors there, that will cancel. And then we have an x squared minus 5x plus 25. So that's going to equal the limit as x approaches negative 5 of the quadratic trinomial x squared minus 5x plus 25. And now let's hope we can do direct substitution. I see a 25 plus a 25 plus another 25. That limit is 75. Number 10, one-sided limits. Okay, well, do we all agree that this expression is undefined when x equals 0 because we cannot divide by 0? But let me show you a little trick where you can use direct substitution with a one-sided limit. And here, all there is to it. So we're going to have a vertical asymptote at x equals 0. And that means there are only two possible solutions here. It's going to be infinity or negative infinity. So the limit of f of x as x approaches 0 from the right could be infinity or negative infinity. So, and again, I've stated this, with one-sided limits, we can often use direct substitution even when approaching a discontinuity. Because look, what's the first term approaching? Well, that's approaching 0. 0 minus. Now, what's the second term approaching? Well, I know x is approaching 0 from the right, so this x cubed is going to be a positive number approaching 0. So what is any real number over a positive number approaching 0? Approaching, that would be infinity. So that is 0 minus infinity or negative infinity, and that was one of our two possible solutions. And there's the graph if you want to check it out there too. Awesome. Okay. Yeah, it looks like we're approaching negative infinity to me. Number 11. Oh, wow. So we got to go back to trigonometry and pre-calculus. And let's see, if I do direct substitution here, by the way, h is approaching 0. So that's sine of pi over 6, which is 1/2. 1/2 minus 1/2 is 0. And that's 0 over 0, indeterminate. So, can I use my sine of alpha plus beta identity right here, which is right down here? Sine of alpha plus or minus beta equals sine of alpha cosine of beta plus or minus cosine of alpha sine of beta. So, let's rewrite it. So, I see a sine of alpha, which would be sine of pi over 6, and then a cosine of the other term, h, and then we have a plus here, so I need a plus here, and then I've got cosine of that pi over 6, and then I've got sine of the h. Okay, so let's think about this. Well, how about our unit circle now? Okay, so this looks easy. All right, see this factor of cosine of h? Sine of pi over 6 is 1/2, so I'm going to go 1/2 cosine of h, or cosine of h divided by 2. And then cosine of pi over 6, all right, that's going to be a root 3 over 2 sine of h minus 1/2. All right, now it's not cleaned up yet enough, but I think, do you see a minus 1/2 out here and a factor of 1/2 right there? So I can factor 1/2 out of the first two terms. I could even factor it out of that middle term too, but I don't think I want to do that because I'd like to use my special trig limits right here, because I see a sine of h over h, and then I think I see a cosine of h minus 1 over h. So let's write this like this. Okay, so let's factor a 1/2 out of the first term and the last term, and that will give me a cosine of h, and then a minus 1/2, a minus 1 right there. Now let's divide this into two separate fractions. So we've got the limit as h approaches 0 of what? 1/2 cosine of h minus 1 over h, and then a root 3 over 2 sine of h over h. Okay, now by our special trig limits, this is approaching 0. 1/2 times 0 is 0. And this is approaching 1. So I have 1 times root 3 over 2 and a root 3 over 2. So I clean that up a little bit so you can see it there. Okay, and then bring the root 3 over 2 out right here. And then the sine of h over h. And again, this is 1 by our special trig limits. And this is 0. So my final answer is still root 3 over 2. Bum, 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 bum. That's cool. All right. Looks like a one-sided limit, so I think I can do this analytically with direct substitution. You know, I'd love to be able to factor this and get a factor of x plus 2, but I don't have a factor of x plus 2. In fact, I don't even know if that's going to be factorable. So f of negative 2, direct substitution, that's going to be a 4 times 2 is 8. Minus 2 is 6 plus 1. That's a 7 over 0. Now that's not indeterminate. All right. So awesome. Direct substitution from one side. I can do this. Okay. So x plus 2. Let's think about it. And again, I already told you I didn't think I could factor that. But I know I'm going to have then a vertical asymptote at x equals negative 2. So right now, I know there's only two possible solutions, positive or negative infinity. Let's use the one-side limit to determine what it is. So when I do my direct substitution, that's what I just verbalized right there. I'm going to go, well, my numerator would still be a 7. And now I've just got to think. I know my divisor is approaching 0, but is it positive or negative? So negative 2 from the left, that'd be like a negative 2.1 plus 2. And this is going to be a negative number approaching 0. Now, this is not real appropriate notation, but I'm going to write this like this. A negative number approaching 0. So a positive real number divided by a negative number approaching 0, that's going to be a negative infinity. And that was one of my two possibilities right there. And there's my graph to determine that too. Look at that, negative infinity right there. All right, well, it looks like we have the same thing here. Because if I do direct substitution, I got a 0 over 0 again. And now x cubed plus 1. I think I could factor this if I wanted to. So I could do it either way. All right, indeterminate form, yeah. So I'm going to do the factoring. So a cubed plus b cubed is going to be, again, a plus b over a squared minus ab plus b squared. So let's factor it. So I've got a plus b becomes x plus 1. And then a squared, x squared, minus 1x, and then b squared, 1. And now my factors of x plus 1 cancel. And I am hoping I can now do direct substitution so I don't even have to think about the one-sided limit. Do you see a negative 1 squared would be a 1 minus a negative 1, that's a 2, plus 1 more, that's a 3. This looks like it's just going to be 1/3. 1/3. Number 14, x squared plus 2x plus 1. Well, that cancels to x plus 1 quantity squared, but those factors don't factor with my x minus 1. So that tells me I'm going to have another vertical asymptote at x equals 1. So the limit then could be, hold it, what did I do? As x approaches -2 from the left, that's a typo right there. That should be a -1 right there. In fact, I'm going to fix this right now in the middle of your video. I hope you guys don't mind. Maybe technology is not working very well here. What was I approaching there? -1? Well, we'll find out in a second. Let's try a -1. Vertical asymptote at x equals 1. I think we're approaching 1 from the left, aren't we? We'll find out though. I'll check it. Yeah, 1 from the left. Okay. Now that might have messed up my covers there, but we'll get through there. Okay, yeah, see, those are messed up a little bit. Can I slide those two just a little bit? I'm going to take a shot at this, you guys. Won't be perfect. Man, they're not wanting to move. All right. Technology never cooperates, so I'm going to leave it as is for now. Okay, so we know that, right? The positive infinity or negative infinity as we're approaching from the left. So let's do this. I'm approaching from the left, so let's do our direct substitution. And 1, that would be a 1 plus 2. That's going to be a 4. And then 1 from the right, that'd be like a 1.1 minus 1. So that's going to be a positive number approaching infinity. How did I get a negative? Because I am approaching 1. Oh, I'm approaching from the left. Excuse me. So that's going to be like a 0.9, 0.99. All right. So if I go 0.9 minus 1, that's negative. So I get negative infinity. Okay. Sorry, I was a little rough on that one, crew. And there's the graph to confirm our solution. All right. Oh, now we get a little crazy here. Now watch this carefully, because we are just simply going back to our special trig limits again. The problem is I've got a sine of 4x, and in my divisor I have a 5x. So I don't want that factor of 5 in the divisor. I want a factor of 4. And if I did direct substitution, I'd have sine of a number approaching 0, 0. And 5 times a number approaching 0, 0, indeterminate form. So there's my special trig limits, and this is what I'm looking for right here. So let's do this. I wish that was a 4. So how about I go, okay, let's multiply by 5 to undo the 5 in the divisor, and then multiply by 4 to get that back. So I need a 5 over 4 right here. Now, I just can't go around multiplying by 5/4, so I had better undo that with a 4/5 out here. There we go. Now, watch what happens when I simplify. So I have, and by the way, let's make this statement. As x approaches 0 from the right, do you all agree that 4x is also approaching 0 from the right? All right, so let's do this. 4/5, and I went from x is approaching 0 from the right to 4x is approaching 0 from the right here. All right, and then I have got my canceling going on right here. The 5's cancel, leaving this sine of 4x over 4x. And what is the limit as 4x approaches 0 from the right of sine of 4x over 4x? Well, that has to be a 1. So 1 times 4 over 5 is 4 over 5. All right. Cosecant. Well, I could probably see this a little better if I did that cosecant as 1 over sine. What do you think? Yep. So let's go 1x, and how about a sine of 2x? Okay. Now, as we are approaching 0 from the right, I'm getting a 1 over, and then the sine of 0 is 0. So this is going to be a vertical asymptote. And the question is, are we going to approach positive or negative infinity? Well, 0 from the right, I'm leaning towards infinity, but let's find out. So direct substitution, do you all see the 1 over 0? Not indeterminate, but I know 0 from the right, I can do this. 1 over, and this factor would be positive, and sine of a number approaching 0 from the right would also be a positive number approaching 0. So that's a positive number approaching 0. So my conjecture was correct. This is going to be infinity. There's a graph, and there you go right there. Sweet, huh? All right. Well, you guys know the routine when we're doing limits, and this is probably indeterminate. Let's check. That'd be a root 3 minus root 3, 0. Yeah, that's 0 over 0. Indeterminate. All right? But when I have at least one radical in two terms, I'm going to drop my radicals with conjugates. Watch this. Okay, what's the conjugate of a minus b? That would be a plus b. So let's multiply by root 2x plus 1 plus root 3. And do that downstairs here, so we're really multiplying by 1. All right, now let's do this multiplication. And up top, I have a minus b times a plus b equals a squared minus b squared. So that's going to be 2x plus 1, a squared. All right, and then we've got minus b squared. Root 3 squared would be 3, minus 3. Okay, and I'm just going to leave this in factored form down here. And I hope I get stuff that cancels here. All right, so let's see. That would be a 2x minus 2. And I don't see anything yet, but now let's factor a 2 out up top. So I'll bring that 2 all the way out. And 2 times what? That would be an x minus a 1. And now the x minus 1's cancel, leaving us this. And now let's hope we can do our direct substitution. So I got the 2, I got the 1. And x is approaching 1 from the right, so that's going to be root 3 plus root 3. That's a 2 root 3. And now the 2's cancel, and I get 1 over root 3, which I am going to write as root 3 over 3. If you wrote this 1 over root 3, I'd have to give you full credit. In fact, if you left it like this, I'd still have to give you full credit. I cannot give you full credit here until you apply the limit. Okay, number 18, that's a floor function or the greatest integer function. And you need to know how to put this into your calculator. Floor function, okay, on your calculator, that is math, and then number 5, which is the integer of, and in this case, that'd be the integer of x plus 3. So the integer part of a number, okay? So put that into your calculator as y sub 1 very carefully. And that's your graph right there. And I did a window so I could see this a little better. Does it look to you like we're going to have a jump discontinuity at every integer? So determine where this function is continuous. Well, jump discontinuities, it's not continuous, but that's at like what, -2, -1, 0, 1, 2, and so on. So there's going to be a jump discontinuity at every integer n. So there exists, see that backwards e, a jump discontinuity at every integer n. So it's non-removable, okay, at every integer n. And that double bar z means the set of integers. And typically, we use an n for the set of integers, so you could actually say at every n. Okay? That's it. So it's continuous everywhere else, but that tells me that. So I could say f is continuous when x is in the real numbers and x does not equal any integer n. I think this is a very appropriate answer right here. Okay, number 19. Well, same thing. Looking for continuity here. Well, let's see. As x approaches 1, what's happening here? So that's going to be a 3. That's a 0 over 0, right? Okay, so we're going to have to probably graph these and take a look at what's going on. Okay, so let's see. Okay, let's clean this up a little bit then. 3x squared minus x minus 2. Let's try to factor that, and let's hope we get a factor of x minus 1, which I bet we will. So I'm going to go a 3x and an x, and that's my 3x squared. And then a negative 2, can I go a plus 2? And a minus 1 here. And if I FOIL that, do you see the negative 3x and the 2x gives me the negative x right there? So that works right there. And now my x minus 1's cancel, and I am left with 3x plus 2. All right, so now let's think about this. That's a 3x plus 2 when x does not equal 1. All right, and it's 0 when x equals 1. So I'm going to see a hole in the graph, all right, because the x minus 1's canceled. So this is a hole, and I think they tried to fill the hole, but they missed, because when x equals 1, 3x plus 2 is not equal to 0. So this is going to be the line 3x plus 2 with a hole in it, and then a dot down below it when x equals 1 at 0. So f of x, there it is right there. And I had to add to my graph because your graph won't show you that hole. But this is 3x plus 2 right here. And there's my hole. Add x equals 1. And when x equals 1, the output is right there. Okay? So let's just describe this. It's defined for all real numbers except when, well, I should say it's continuous for all real numbers except when x equals 1. So this is a removable discontinuity at x equals 1. And I want to say it like this. F is continuous when x is in the real numbers as long as x does not equal 1. That's what I'm looking for. All right, number 20. Describe any discontinuities of the given function. Well, here we go. Do you guys see an asymptote at x equals 2? Vertical asymptote at x equals 2, okay, which is obviously a non-removable. But if you just told me this right here, I know it's non-removable. Okay, same thing, vertical asymptote at x equals negative 1. That would be fine. By the way, that is non-removable. Okay, cosecant, well, you know cosecant has infinitely many asymptotes, so we're going to have to play with this a little bit to describe it. You know I'm going to go 1 over sine, all right? And I know sine of pi x over 2 cannot equal 0. And I also know that sine has an output of 0 at any multiple of pi. So that means that this baby right here, vertical asymptotes at x equals, well, let's think about this now a second. Pi over x over 2 cannot equal any multiple of pi. And I'm going to describe that with an n pi. Now, can I just take this and cancel my pi's, divide both sides by pi, like that? And then look at what this says. N cannot equal x over 2. Solve for x, that means x cannot equal 2n. All right? So that would be x cannot equal any even integer. Oh, that's cool. So let's go here. X cannot equal any even integer 2n. That's what that means right there, because n can be any integer like negative 1 or negative 2. So 2 times negative 1 is negative 2. 2 times 0 is 0, and so on. So vertical asymptotes at every even integer. Wow, That's a cool problem. Non-removable discontinuities at each even integer, definition of even right there. And you could have just left it right here in red. Okay. Determine the value of c such that the function is continuous. Okay, so we're going to have to make this compound function continuous right here. All right, which means, well, look at here. It's x plus 3 when x is less than or equal to 2, and it's cx plus 6 when x is greater than 2. So we're just going to do direct substitution, x equals 2, set up the equation, and solve for c. Just like this. So I'm going to say x plus 3, that's what I just verbalized, x plus 3, oh, and I did the 2 for the x, has to equal 2c plus 6. Okay, solve for the c. So that implies, booyah, well, what would I have? A 5 minus 6 is negative 1 equals 2c. So divide by 2 and c equals negative 1/2. So if I let this c right here equal negative 1/2, this compound function would be continuous. All right. $5,000 in a plan at 12% semi-annually, and they give me the function. Graph the function and discuss its discontinuities. So again, do you notice that we have the greatest integer function right there, or the integer part of a number? So they just want you to be able to put this into your calculator correctly. All right. And by the way, you saw this formula in pre-calculus without using this floor function business. In pre-calculus, it looked like that right there. But let's just take what they gave us and put this into our calculator very carefully. So I put it in using my greatest integer function. That's that math 5, remember? So 5,000 times 1.06 to the integer part of 2 times x. Okay? And looks like I did a window 0 to 4, and then I probably did a zoom fit to get this part. And there's my graph right there. Okay, so it looks to me like there's a discontinuity at every 1/2. Okay, every multiple of 1/2. So how are we going to describe this? Let's go. Non-removable jump at x equals any over 2. Let's go. N over 2, where n is in the set of integers. Positive integers there. You see 1/2, 1, 3/2, 2, and so on. Okay. Oh, now this gets easy. Find the vertical asymptotes. Well, can't divide by 0, so there's a vertical asymptote at x equals 0. Oh, you want lots of those. How about this one? A vertical asymptote at x equals 10. This is some of the easy stuff I was telling you about. All right. Oh, look at this. The cost C in dollars of removing P% of the air pollutants in the stack emissions is C equals 80,000 P over 100 minus P, and P is in the closed interval from 0 to 100. Find the cost of removing 15%, 50%, and 90% of those emissions, and then find the limit of C as P approaches 100%. Okay, so again, this is P%, so we're going to put this into our calculator as a y sub 1 and just let that P equal an x. Okay, and now we need to approach, well here, no, I'm going to have my independent variable at s, so I can put directly 15%. And again, I'm not going to go 0.15. That's 15% as it's defined. So I'm just going to go x equals 15. And I get $14,118. At 50%, I get $80,000. This is getting expensive. Ooh, 90%. I wonder what that's going to be. That is going to be $720,000. Now, does it look to you like we're going to approach anything? I'm going to conjecture right here that I could never get 100% of the emissions out of the air from this factory situation right here. So I'm going to say as P approaches 100%, my cost is going to approach infinity. Watch, I just picked some numbers. I probably did like 95, I don't know, 98, 99, and then even closer. Yeah, that's exactly what I did. 95, 98, 99, 99.99. Now let's look what's happening here. Ooh, 1.52 times 10 to the 6, 3.92 times 10 to the 6, 7.92 times 10 to the 6, and then 8 times 10 to the 6. Those numbers are getting very, very big. So I'm going to say we are diverging to infinity. The limit of C of P, as P approaches 100 from the left, is going to be positive infinity. You just put an infinity there too. Okay, 28. Oh man, they're getting tough on us here, man. Tangent of 2x over x, as x cannot equal 0. So we're going to find the limit of tangent of 2x over x as x approaches 0. Can be defined so it's continuous at x equals 0. Oh, CANF, that's what. Well, first we better find this limit here. Okay? All right. So if I do direct substitution, tangent of a number approaching 0 is 0. And x is approaching, so that's indeterminate form. All right. So, I did a really nice graph. I think I did this like in Desmos. All right, but you could do this right on your calculator. Please make sure you're in radian mode. And I think I can clearly see my limit as x approaches 0, while the left hand and the right hand would both be approaching 2. So there's the answer to the first part. The limit of tangent of 2x over x as x approaches 0 appears to be 2. Okay, now, can f be defined so it's continuous at x equals 0? Well, you know there's a hole there, right? Because of that divisor right there. So we're just going to do a compound equation. And when x is approaching 0, we're going to define that as a 2. So let's do this like this. We're going to call this f of x equals, and let's go ahead and go tangent of 2x over x when x does not equal 0. Okay, and then plug the hole right here. So we're going to throw the constant 2 when x equals 0, and that is how we plug a hole or make a function that has a hole, discontinuity, which is removable, continuous. Very cool. All right. Determine whether the statement is true or false. If it's false, show why. The limit of f of x as x approaches 2 equals 3, where f of x is going to be 3 when x is less than or equal to. So we're constant and 3, and 0 when x is greater than 2. Well, that's false because what? Greater than 2? We are, the right-hand limit is 0, and the left-hand limit is going to be a 3. It's false. The left-hand limit does not equal the right-hand limit. Okay? And now 30. The limit of f of x equals 1, which is constant as x approaches 3, where, okay, here we go, x minus 2 when x is less than or equal to 3, and then negative x squared plus 8x minus 14 when x is greater than 3. So this one I bet is going to be true. Let's just try direct substitution here. So 3 minus 2 is 1. And then that would be a negative 9 plus 24. And that would be what? 15 minus 14 is 1. So with direct substitution, I get 1 with both of these parts of the compound function. So I'm going to say that's a true statement. Chew. And if I remember right, I think I put 30 problems on this. I won't have 30 problems on the test, but I hope this worked out for you, and I hope you guys enjoyed it. I'm sorry my voice was a little rough today because of coaching Friday night. It's now Sunday afternoon, but not too bad. All right. Have a great day. Let me know if you got some questions.